Hi everyone. In this video I'll be talking about 10.2. We're evaluating and graphing exponential functions. So here is our kind of formal statement. An exponential function with base b, and the exponent, notice the variables up here in the exponent, so that's why we call this exponential. We have that b needs to be positive, but that b cannot be 1. I encourage you to investigate when b is 1, why that is not exponential. Here are some exponential functions first, and some not exponential functions. So 2 to the x is exponential, where the base is b equals 2. Here's an exponential base of 5 raised to the 3x. This is exponential. Here's 9 raised to the x plus 1. That is exponential. Here is 1/3 raised to the 2x minus 7. That's exponential. So the base would be 1/3 there, which is totally fine. We need that the base is greater than 0 but not equal to 1. Here are some non-examples. 1 to the x, that is not exponential. And if you use the point plotting method, maybe you can see why that's not exponential. -2 to the 2x, the base needs to be positive. So that's why this one is not exponential. X to the x, the base needs to be a number. It can't be the variable. So what I've been stressing for a large part of this semester regarding graphing is point plotting. You can always use the point plotting method to graph things. So for this one, that's exactly what I'm going to do, is I'm going to plug x's in, and then I'll calculate f of x. This will be for part 1. So maybe I'll use -2, -1, 0, 1, and 2. So I'm plugging these into x. So 3 to the -2, that's the same as 1/3 squared. That's the same as 1/9. 3 to the -1, that's the same as 1/3 to the first, in other words, 1/3. 3 to the 0 is 1. 3 to the first is 3. 3 squared is 9. Point plotting method. So I can plot these. Here I have -2, and then for 1/9 I'll just go a little bit above. This is kind of like a micro graph here, but -1, we have 1/3, so I'll just go a little bit more above. 0, we're at 1. 1, we're at 3. And then 2, we're at 9. So we'd have those 5 points, and then I'll go ahead and just make this curve. So you kind of get this hockey stick appearance. So this thing is growing exponentially. What about for part 2? Maybe I'll use another sheet of paper to show you that. I'll try to find a blank sheet of paper. So for the point plotting method on that one, so we'd have part 2 as f of x equals 1/3 raised to the x. So you can definitely use the point plotting method here as well. So I'll just stick with the same x's. Okay, so plugging in -2, I have 1/3 raised to the -2. If you don't know what that is, your calculator does. Parentheses, 1/3, end parentheses, raised to the -2. It equals, this should say 9 on it. Then 1/3 raised to the -1. Change this -2 to -1. It equals, this should say 3 on it. 1/3 to the 0 is 1. 1/3 to the first is 1/3. 1/3 squared is 1/9. So now I'll take these values and I'll plot those on the graph. So I'll take these outputs and I'll plot them over here. So let's see, this is really difficult to do. So I'm just going to show you these I have -2 and 9, so -2 and 9. -2 and 9 right there. -1 and 1/3. Sorry, -1 and 3, right? I'm looking at these values down here, but I'm not able to get those in the screen at the same time as the graph. This is one of the fun things about doing this. -1 and 3, 0 and 1, 1 and 1/3, 2 and 1/9. So I get this, what is called decay, exponential decay. All right, so comparatively, this one is growth, and this one is what we call actually decay. So when the base is between 0 and 1, you'll get decay. When the base is greater than 1, you'll get growth. Going on to part 2 here. So how might I graph this? Point plotting method. It always works. Plug in some x's, graph the y's, plot the points, draw the line. So -2, -1, 0, 1, and 2. I'll plug that in for x here. So 4 to the -2. 4 raised to the -2, 1/16. 4 raised to the -1, 1/4. 4 raised to the 0, 1. 4 to the first, 4. 4 squared, 16. So at -2, we had 1/16. I'm not going to be able to do better than that. -1, 1/4. Okay. 0, 1. 1, 4. And then 2/16, it looks like I just need to estimate right about there. So here's exponential growth. And it's growing faster than our previous one because of this base being 4 instead of 3. For the other one, so I'll look at values for this. So maybe I'll try to squeeze that here this time. So x and then g of x. So I'll have -2, -1, 0, 1, and 2. So 4 to the -2 plus 3. Here's 4 to the -2, I just need to add 3. So that would be about 3.06. Okay, -1. So replace -2 with -1. That's about 3.25. Replace x with a 0. So 4 to the 0 plus 3. This is now 4. 4 to the first plus 3. This is 7. 4 squared plus 3. This is 19. Okay, so here are our values. So at -2, we're a little over 3. Right about there. -1, we're a little bit more over 3. 0, we're at 4. 1, we're at 7. And 2, we're at 19. So, should have kind of drawn it more this way, but that's okay. All right, next one. So what about solving equations? We're going to want to be able to solve exponential equations. There's one technique that will work sometimes. It is this technique. So in certain rare cases, it's not going to be rare in example 3, but in general, this is a rare thing. So when you can rewrite both sides as the same base, then you can just simply set the exponents equal and solve. So if I'm trying to figure out what x makes this also 125, what I can do is think of 125, luckily, as a base 5. So 5 cubed is the same as 125. What this is saying is once you have the bases the same, m and n are the powers, I just need to set m equal to n. So 3x minus 6 needs to be equal to 3. That's all this thing is saying. And solve for x. So 3x equals 9, divide by 3. So we get a 3. You can definitely check all these, right? Just like with any equation that you're solving. So 5 raised to the 3 times 3 minus 6, are you equal to 125? So 5 raised to the 3 times 3 minus 6, this is 125. So that checks out. In some cases, you'll need to actually change both sides. So I can't change a 32 into a base 4 that easily, but 4 I can change into a base 2. So 2 squared is the same as 4. And then if I raise that to the x, that'll be the same as 4 to the x. And 2 to the 5th is the same as 32. So powers to powers multiply. In other words, we have 2 raised to the 2x equals 2 to the 5th. Once the bases are the same, you can just set the powers equal. So we need that 2x equals 5. So divide by 2. So x equals 5 halves. All right, on to page 149. So compound interest. This is another exponential application here. So banks, basically, when you deposit money, let's say you deposit, let's say, I don't know, if someone passes away and you inherit 10 grand, $10,000, and you say, you know what, I'm going to invest this 10,000, and you take it to a bank and you say, I want to invest this, and then they give you some rate. So what they're going to do is they're going to take your money from you. They're going to say, thank you for that $10,000. And then what they're going to do with your $10,000 is they're going to loan it out to other people. And what they're going to do on those accounts is they're going to charge those people interest. So they're basically making money using your money. So they're happy to give you a little bit of a cut of that, just so you're incentivized to give them even more money. Okay, so if you deposit that $10,000 and then you come back next week and say, hey, I want my $10,000 back, they actually might need a little bit of time to gather your money because they've lent it out. So they might say, okay, we'll get the 10,000, but give us 3 days. So it's not as though your money, if you're a millionaire, your money isn't just sitting in there. It's being lent out to people, and they're making money off your money. And that's the business of a bank. So in certain cases, they'll give you like a compounding period. Say, we're going to increase your money every quarter or every month or all the time, continuously compound your money. So that's what this formula is about, these two formulas. So this one will be for continuous, and you can also tell that because it's written over here. And this will be for some amount of n periods. So for this first one, it says, Angela invested $15,000 in a savings account. If the interest rate is 4%, how much will be in the account in 10 years by each of the following methods of compounding? All right, so it says, what about if money is compounded quarterly? So in this formula, P is the principal, that's the amount that you invest. R is the interest rate that you're given. N is the number of compounding periods in 1 year. And T is the number of years that you're investing. So for Angela's amount, her amount would depend on that 15,000. So maybe I'll write over here first. I'll kind of identify things. So we have P is this 15,000. We have R, which is 4%. We have T is 10 years. So I'm just kind of identifying everything. And then for this first case, since it's quarterly, that means N will be 4, since there's 4 quarters in the year. So I'll have 15,000 times 1 plus 4% over 4, raised to the 4 times 10. All right, so I'll go ahead and type this in now. So 15,000 times parentheses 1 plus fraction, so 4, and then I need to find the percent symbol, which is actually right here. So this is behind the left parentheses. So I'll go shift left parentheses for that percent symbol, over 4, raised to the 4 times 10. So this would be the amount of money that she would receive. I'll go ahead and round this to the nearest penny. So this would be about equal to 22,332.96. So in 10 years, her money would have grown from 15,000 to a little over 22,000. What if it's compounded monthly? So everything else we're assuming is the same. So we still have P equals 15,000. We still have the interest rate that was quoted, 4%. We have the time still is 10 years, except monthly means N will be 12. So N always counts the number of compounding periods in just 1 year. So the amount for this arrangement would be 15,000 times 1 plus 4% over 12 raised to the 12 times 10. So from before, I can just get rid of the 4s here and here and replace those with 12s. So this would be her amount in that case. So 22,362 and then 0.49 for 49 cents. For continuously compounding, we're now no longer using this formula. Continuous compounding means we're using this formula here. So P is still assumed to be this 15,000, right? And for A equals P times E raised to the RT, we just need R and T. R is 4%, and T is still this 10 years. So let's see what the amount would be. So 15,000 times E raised to the 4% times 10. So that E is a known number. That's Euler's number. So times, and then on my calculator to find E, it's down here. This is one way to locate it. There's also one over here. It's that important. It's 2 places. So I'll actually use this button. So I'll go Shift. Now I have E raised to the 4%. Make sure you have that percent symbol there. It's a big difference if you don't have it. So this is 22,377. .37. I'm going on to page 151. This will be the last one I do in this video. So exponential growth and decay. So let's see, it says Salma is a researcher at the Center for Disease Control and Prevention. She is studying the growth of bacteria. She starts her experiment with 50 bacteria, which grow at a rate of 15% per hour. How many bacteria will she find after 8 hours? Okay. So we have 50 bacteria at the beginning. So this will be this thing here. So the original amount A sub 0, so that 50 goes in here. So A sub 0, sometimes called A naught, or the initial amount, would be 50. Okay, the rate would be this 15%. So we'd have 15% as the growth rate. And then it looks like we're looking for a time of 8 hours. So you'd have the amount of bacteria as 50 times E raised to the 15% times 8. So I can actually just edit what I had previously. So I can press left, change that to 50, change the 4% to 15, make sure I still have the percent symbol, change the 10 to an 8. So she would see 166 bacteria. All right, talk to you guys next time.